So in this second video of relativity, we've got a bit to cover. So you need to know that in relativistic mechanics, so relativistic means really high speeds, there is no absolute length or time interval. So length contracts and time dilates. Now you will watch that video about simultaneity. So two events that appear simultaneous for a stationary observer may not actually be for that observer that is in motion. You need to know that relativistic speeds, time can be dilated, and you need to be able to solve calculations involving this. And I'll unpack this, and this here is called the Lorentz factor, and we'll talk about that soon. You need to be able to solve problems involving both of these equations, and you need to be able to explain the effects of time dilation on objects moving at relativistic, really fast speeds. So, you would have watched the train video. So, as you now know, it's perfectly acceptable that two events that are simultaneous in one frame of reference, so the person observing the train being struck by lightning from the front and the back, they observed those two events simultaneous, the exact same time. The light reached the stationary observer's eyes at the exact same time, so he thought they were simultaneous. And those two events that are simultaneous in one frame of reference may not be for that observer in motion. So the person on the train, they actually saw the lightning strike the front of the train first, and it got to them quicker, whereas the train was moving away, and the back strike, they observed it as taking longer to reach them. And that's perfectly fine. So that's the concept of simultaneity. Two events that are simultaneous for one observer may not be for an observer in motion. Now, time dilation. Now, the reason for that different events being observed from different frames of reference is that time can actually be dilated or stretched or increased. Basically, time dilation refers to that slowing down of clocks that are in motion relative to an observer. So, person on Earth, if they're observing someone moving at really, really high speeds, so the person on the spaceship, their, time's going by as normal, clocks appearing to appear as normal. But for that stationary observer observing that that spaceship going at relativistic speeds, they're actually seeing this clock run slower. And later on, we'll talk about the applications of this and space travel. Now, consider the problem below. On this first image, A, we have just a person observing a light beam going upwards and forwards. They're seeing it being reflected straight up and straight down. But someone observing this same spaceship, they're seeing the light travel a far greater distance, because relative to them, the light is bouncing up and then going across. The light is traveling a much larger distance. Now, I'm not going to bore you with the details, but there is a derivation on page 97, but it is very complicated and you do not need to know it. But it's on page 97 in your textbook if you really want to have a read through. But it proves the following. Basically, we can relate this time to the time it would take for this using Pythagoras' theorem and do a bit of rearranging, and eventually we get the following expression. That time, t, is equal to t naught over the following. Now, usually this is broken up into two equations, which is that the time is equal to the Lorentz factor times by t naught. And I'll explain what t and t naught are in a second and in more detail on the next slide. But this is the Lorentz factor. That is on your formula sheet as the Lorentz factor. And t equals Lorentz factor times t naught is also on your formula sheet. So this one and this one are on your formula sheet. This is known as the Lorentz factor. Basically, also on your formula sheet is a definition for t naught. And Sayce's definition for t naught is the following. T naught is a time interval in the moving frame of reference. So t naught is the time interval in the moving frame of reference. So if we go back to our spaceship, t naught is the time interval in the moving frame of reference. So t naught is the time interval in this frame of reference here. This person here is observing it in the moving frame of reference. Now, I don't love that definition that Sayce have written on the formula sheet. I prefer to think of it, and the textbook does as well, as the proper time. So if you're on the spaceship, the time you observe this to go up and down is t naught. So it's the proper time. It's the time that it actually takes if someone was stationary on the spaceship. So in this scenario below, t naught would be the observer on the spaceship. It's always a time measured in the reference frame in which the event is at rest. So if you're on the spaceship, you're at rest with the light beam going backwards and forwards. And the time it takes to go backwards and forwards, that will be t naught, and that's going to be the shortest time that anyone could record the event. It's the true time. Whereas t, that's the time interval it would take if someone was stationary and was observing this spaceship. They're seeing, because light's traveling a far greater distance for them, because space and time is relative to this. They're seeing the light go up and back, and it's taking longer. So this time here, so this t is the time interval in the stationary observer's frame of reference. In this scenario, it's a stationary observer on the planet, and they see that time being dilated or slowed down, and hence t is always going to be the longest time that someone could record an event. That's probably the easiest way to think of it. T naught is the shortest time someone could record the event, someone that is at rest with the event, whereas t is the time that is the longest time. It's the time that has been dilated, so it's always going to be the longest time. And because this spaceship's moving at such high speed, time is slowing down, and so realistically it looks like it's taking longer to complete the same event. Now, the Lorentz factor, that just basically indicates, it basically takes into account only how fast an object is moving. So it takes in, it's actually the relative velocity between two inertial frames. So it takes into account the velocity difference. So something could be stationary and something could be moving, or something could be moving and something could be stationary. It's the change in speed between them, the relative velocity. And it's basically a ratio, and it takes into account the speed difference between them and the speed of light, and this. It was using Pythagoras' theorem, the reason this comes out. Basically, it gives us a value from 1 up to 10-ish. And basically 1 means you're traveling at a slow speed, and 10 means you're traveling at basically the speed of light. And we're going to use this Lorentz factor for doing calculations involving time, length, and mass later on. But for now, we're just looking at time. So this is going to dilate time. So it's important that v is the velocity of the moving reference frame of the relative velocities between the two reference frames, and c is the speed of light. And the speed of light is 3 times 10 to the 8, which we should know. Now, graphically, this is a graphical. So if the speed of light is, very low, this is the ratio between speed and speed of light. So if this is 1, it means that it's c over c, so we're traveling at the speed of light here. So at 0.1, the speed of light, the Lorentz factor is 1. So basically, there's no time dilation. All the way up here, even here, there's barely minimal any time dilation, and that's 0.3 the speed of light, so that's insanely fast. 50% of the speed of light, we're only getting a tiny bit of time dilation. So 1 second would only be like 1.1 something seconds. And then, realistically, as we're getting faster and faster, so 60% speed of light, 70% speed of light, 80% speed of light, 90% speed of light, 95% speed of light, we're getting some significant time dilation. So at low speeds, there's no time dilation. We're not going to, traveling at 200 k's per hour in a car, we're going to have minimal time dilation. We're not going to notice it on Earth. So some calculations involving the Lorentz factor. I'll quickly do them. But realistically, you need to use your calculators. Make sure you can do these. These are just work examples from your textbook, but I'll just go through them quickly. So, question 1. Calculate the Lorentz factor for an object traveling at a speed of 0.4 the speed of light. So 0.4c just means 40% of the speed of light to 3 significant figures. So Lorentz factor is the following formula. It's just 1 over 1 take speed of light squared, which in this case, the velocity squared, which in this case is 0.4, the speed of light squared, over the speed of light squared. And if we were to simplify this, we're going to have 1 over the square root of 1, well, my pen is being horrible, 1 take, and if you square this, 0.4c squared is 0.4 times 0.4, which is 0.4 squared, times by c squared. So it's going to be 0.4 squared times by c squared over c squared, and guess what? The c's cancel. So we're left with an expression which is 1 over the square root of 1 take 0.4 squared. And if you type this into your calculator, you will get 1.09. So traveling at 40% the speed of light, we're going to have a Lorentz factor of 1.09. So only about a 9% increase. So time's only dilated about 9%, which isn't super significant, especially when you're traveling at 40% the speed of light. Now, you can also just be given a speed that you're traveling at. So the Lorentz factor for an object traveling at 2.4 times 10 to the 8. So that's 80. That's 80% of the speed of light. So it's pretty fast. So it would be 1 take 2.4 times 10 to the 8 squared divided by 3 times 10 to the 8 squared, because that's the speed of light. And if you type that into your calculator, you'll get a Lorentz factor of 1.7. Now, show that a time interval of 1 second, as measured by an observer on a spaceship moving at 98% the speed of light, is approximately 5 seconds as measured by a stationary observer on a nearby planet. So first, we need to calculate the Lorentz factor. So the Lorentz factor for an object moving at 98% the speed of light so that's going to give us 1 over 1 take 0.98 squared, because the c's will cancel, and that'll give us a Lorentz factor of 5.03. And then to find the time taken, well, that time as measured by that stationary observer, it's obviously going to be dilated, so it's going to be the Lorentz factor, which is 5.03 multiplied by the proper time, which was 1 second as measured on that by that observer on that spaceship. And to two significant figures, 5.03 times 1 will just be 5 seconds as required. So if you're moving at a very high speed, 98% the speed of light, which we can't go anywhere near, but if you could, time dilation is going to be massive, and we'll talk about that in a minute when we talk about the twin paradox. Question 4. An unstable particle has a lifetime of 3.8 times 10 to the minus 8 seconds, so it's only stable for a fraction of a second. And that spaceship is traveling at 95% the speed of light. Calculate the lifetime of the unstable particle as measured by a stationary observer on a nearby space station. So again, Lorentz factor, 1 over 1 take, and this time it's 95%, so I'm just going to skip to 0.95 squared, just to save time. And that'll be 3.2, the Lorentz factor. So it's still significant. Some significant time dilation at 95% the speed of light. And then the time is obviously just the Lorentz factor times by the proper time, which is 3.8 times 10 to the minus 8. And so the time as measured on the nearby space station has actually increased and dilated the time to 1.2 times 10 to the negative 7 seconds. Last calculation example. So an observer sets up an experiment in a lab, records the period of the pendulum to be 2.2 seconds. A secondary observer moving at a high speed records the period of the pendulum to be 3.3 seconds. So so state with reason which one of the two observers records the proper time. So the proper time is T0, remember? And the easiest way for you guys to remember the proper time, or T0, is the smallest one. So state with reason which one of the two observers records the proper time. So the person in the lab. Because they are recording the shortest time and hence the time taken at rest with the event. So determine the relative velocity between the two observers. So we're not told we're not told the speed between them. We're not told the speed between them at all. So what we can do though is the following. What do we have? We have the proper time T0, and we have the time as observed by the moving observer. So we've got T, the dilated time. And we want to find the relative velocity between the two observers, the difference in velocity between them. So we want to find V. So in order to find V, we need speed of light, which we know, the Lorentz factor, which we don't know, but we can figure it out because we know the proper time and we know the dilated time. So we can rearrange this and we can get the Lorentz factor is the dilated time divided by the proper time, which will be 3.3 divided by 2.2, which will give us a Lorentz factor of 1.5. Now, this is the tricky part, and not scarily, they did actually put this in one of the recent exams, where you had to rearrange this equation for V. So you could be asked to do that. So let's work through it step by step. It's a tough one to rearrange though, but they have actually got students to do it before, so we need to go through it. So we eventually want to rearrange this equation for V. So there's a lot we need to rearrange and get rid of to get V by itself. First things first, we want to get rid of this square root sign. So we're going to square everything. So we'll have the Lorentz factor squared. We can square 1, which will just give us 1. And then we're going to square the denominator, which will just leave us with 1 take speed squared over speed of light squared. Now, we want to get V by itself. So the next step that I would recommend you doing is swapping these, because we want to get V on a numerator. So we're going to swap these, and that's going to lead us to having 1 take V squared over C squared equal to 1 over the Lorentz factor squared. Now, we've still got a fair bit to get rid of here. So what we can do is we can do the following. We want V to be positive eventually. So what we can do is we can add V squared over C squared to both sides. It'll cancel on this side, and we'll be left with V squared over C squared on this side of the equation. And then we would have plus 1 over the Lorentz factor squared. So we want to get rid of this, so we'd take that from both sides. So now we're going to take that, and we'll have take 1 over the Lorentz factor squared. If I've done too many steps in one, it's because I'm running out of room on the PowerPoint. see me if you need help with this rearrangement. And then finally, we want to get v by itself, so we're going to times both sides of the equation by c squared. So we'll have c squared times by this entire side of the equation, so 1 take 1 over the Lorentz factor squared, equal to v squared, but we don't want v squared, we want v. So we're also going to square root both sides of the equation. So finally, we can figure out the relative velocity between these two observers, and it's going to be the square root of, the speed of light squared, which is 3 times 10 to the 8 meters per second squared, meters per second, and then square it, times by 1 take 1 over 1.5 squared. And if you type that all into your calculator, you'll get the relative velocity of, where did I do it? I typed it in. So you get v equal to 2.24 times 10 to the 8 meters per second. Now, just a quick little application. It's not actually part of the course, but it's fun to think about. Imagine two twins. One remains on Earth, the other travels to some sort of distant star system, planet, whatever, and they're traveling at very high speeds. So the twin on Earth, the stationary observer observing their twin, would observe the twin's clock running much slower, okay? Much slower. Now, in example 3, if we go back at 0.98, so 98% the speed of light, we had a Lorentz factor of 5.03. So approximately 5 seconds on Earth would equal 1 second on the rocket, the spaceship. So, what does this mean? Well, imagine both the twins. They're both 30 when they both set off. Okay? Now, the person going up into space, the astronaut, they're only going to measure that 10 years have passed on the spacecraft. However, their twin, is actually going to have lived for 5 times that amount on Earth. So if they've observed 10 years on the spacecraft, traveling at 98% the speed of light, when they get back to Earth, on Earth, 50 years is going to have passed. So when the twin returns, because he was traveling so fast, he's only 40, because he's only increased by 10 years, whilst his twin is actually going to be 80 years old because time dilated based on, so he was a stationary observer and time has dilated based on the moving spaceship. The big picture is that if we do eventually reach really fast speeds and we can travel to different solar systems, then basically people that do travel and set out on these voyages and expeditions, well, when they return, they're going to possibly their friends and family are going to have aged back on Earth, and you're going to come back and they might have passed away and be long gone. So that's a consequence for space travel. So it's not part of the course, but it's a cool thing to think about. Now I want you guys to do questions 5 to 9 in the Essentials textbook. Thank you.